Hello, everyone, and welcome to the next installment of Journal Club. My name is James Mattei, and I'm excited to share this paper with you all today. Today's paper is called Latent Collaboration in Multi-Agent Systems. This paper investigates how we can improve efficiency in multi-agent systems by changing how information is passed from one agent to the next. Instead of translating the embeddings back into text before passing to the next agent, the authors investigate how to share the last layer embeddings of each agent, thereby reducing the computational and inference costs of multi-agent pipelines. But before I get too far ahead of myself, let's cover some key background info so that we're all on the same page. First, we need to talk about what an embedding actually is and how LLMs go from text input to text output. As with most machine learning techniques, LLMs do not actually operate on the text itself. When a model is thinking about a question, it's actually processing millions, if not billions, of numerical representations of the text. This includes the system prompt and instructions to the model, as well as the specific question it was asked. To translate the text into these numerical representations, LLMs make use of an embedding model, which is a technique from natural language processing to turn each token into a long vector of numbers, representing that specific piece of text. These vectors typically range from several hundred numbers to a few thousand. For example, Llama 3, their 8 billion parameter model, uses 4096 dimensional vector as it passes through the layers of the model. So, after the LLM processes your input across these vectors, the model takes the final vector and passes it through a language modeling head that projects that single vector of numbers into a massive list of scores, one for every single word or potential token in the model's entire vocabulary. Those raw scores are a little hard to interpret altogether, so the model uses a function called softmax to translate the scores into probabilities, signifying how likely that word is to appear next. Lastly, the model chooses from this distribution of words to select the next one to appear in the output. For the sake of time, I'm giving a very high-level explanation here, but if you're curious to learn more about the inner workings of LLMs, be on the lookout for my blog on this topic coming soon. So now let's talk about multi-agent systems a bit. While frontier models are incredibly capable, they can struggle with long, complex workflows. Multi-agent systems solve this issue by breaking up a large problem into smaller, manageable subtasks. By giving an agent a narrow persona, like a critic or a coder, we can significantly improve the accuracy and quality of the final output. There are several multi-agent architectures, really the sky's the limit in terms of creativity, but the most common ones and the ones that the authors investigate are sequential and hierarchical mass. So for sequential mass in the paper, it consisted of 4 LLM agents. These agents assume complementary reasoning roles to each other and are organized in a sequential pipeline, where the output from one agent, along with the original question, feeds in as input to the next agent in the pipeline. In the hierarchical mass, multiple LLM agents operate as different domain experts simultaneously. Each agent independently reasons over the question from its disciplinary perspective, and then a summarizer agent receives all outputs along with the initial question and synthesizes the final answer. So let's take a deeper look at the sequential mass model and see how these agents actually communicate with each other in practice. So this may look like a seamless flow of information, but if we peek under the hood at the handoff points, we find a significant amount of computational busy work that happens every time one agent finishes a task and passes it on to the next. Let's look at this first handoff from the planner. Internally, the planner doesn't think in words, right? It thinks in those high-dimensional vector embeddings that we talked about earlier. So remember all this? To communicate with the next agent, the planner has to unembed those vectors, translate them into a probability distribution, and finally output string-based text. Then the critic has to take that text and re-embed it back into vectors to begin processing the information. This happens again between the critic and the refiner, and again between the refiner and the solver. We are constantly translating from vector to text and back to vector again and again at each agent handoff. In a system with 4 or 5 agents, this duplicate work can lead to a couple of issues. First and foremost is latency. Each translation and handoff between agents must wait for the entire compute process to finish. If you chain enough of these agents together, you could be waiting quite a long time to get a response back. And the second issue is information loss. So very similar to a game of telephone, nuances in the original vector representation from the first agent can be lost when they're flattened back to text, only to then be slightly misinterpreted when re-embedded by the next agent. I found a great visual example of this on Reddit. Someone asked ChatGPT to recreate this image of Dwayne Johnson 100 times without making any changes. So here's where we started, relatively normal image, and here's where we ended. Obviously, some things here were lost in translation during those 100 handoffs from agent to agent, and the same thing happens in other mass systems when operating on texts, maybe to a lesser comical degree than this. So how can we improve upon this system and make it so that we only have to embed the input text once at the start and unembed the vectors once for the final output? The authors proposed their system called latent mass. So instead of translating the output of one agent back into text, the authors propose using those latent vector embeddings at the last layer of the previous agent and providing that along with the initial prompt as input to the next agent. By utilizing this latent communication, we can completely avoid all of that duplicate work I was describing earlier, translating the vectors back into text and into vectors again. The next agent can effectively pick up right where the previous one left off with the full embedding and details and context. So in practice, this process is a bit more complicated than it may sound. So first, the input embeddings, which contain the system prompt and the question, are passed through the transformer layers of the agent as normal to compute the last layer representations, which we refer to as H. Next, instead of decoding the next token selection process, that diagram from earlier, H is used as a new input embeddings for the agent. This process is repeated for M latent steps until we get the set of all of the last hidden layer states, capital H. These latent thoughts that are generated by the first agent. The newly generated latent thoughts and the original input are used to populate a key value cache that will serve as the working memory for the first agent. And lastly, that working memory computed by the first agent is concatenated with the next agent's key value cache. This ensures that the new latent thoughts generated by the second agent are conditioned on both the working memory of the previous agent and its own internal representations and instructions. Now, some of you may be asking, if these models are trained to receive text as input, will the second agent really be able to accept latent embeddings with the thoughts of another agent out of the box and be able to have the same performance? And the answer is no, obviously. So there's a key step, and the last piece is to perform a linear alignment using a projection matrix that maps each output vector of the latent thoughts to a new input vector that more closely aligns with a valid input that the agent would expect to receive. To evaluate their technique, the authors used some of the Qwen3 models and compared it against single agent setups and a traditional textual multi-agent system. Across nearly every benchmark that they tried, latent mass saw massive improvements in both token usage and inference speed. The gains were consistent in both sequential mass and hierarchical mass settings. Additionally, across the majority of the tasks, the final accuracy percentage of latent mass was better than either the single agent or text mass setups. The cherry on top is that their technique did not require any fine-tuning or retraining of the models. Very impressive stuff. Now, I really wish the authors had a section on the limitations of their research, especially because the presented improvements are so impressive. But from what I can gather in my understanding, this technique will only really work if all of your agents in your pipeline are the same model. So if for some reason you wanted to have maybe Claude as your code expert and Gemini as your science expert, the different models would have different internal representations of their latent thoughts, and it would not necessarily be compatible with this technique. So if you remove the plain text communication between the models, you will essentially be flying blind. You'll have no way to audit mid-flight and see if your agents have deviated from their intended behavior until that final answer is presented. And depending on your task or how complicated your system design is, it won't really be clear which agents may have gone off the rails. As always, please check out the paper yourself for a lot of the details that I had to skip and I wasn't able to cover here. And please comment or email me with any questions that you may have. Thanks for watching.